Hello everyone. Today we're tackling problem number 14, linear regression using normal equation. So here we're given two inputs, one which is going to be x, those are the independent variables of a linear regression, and y, which is going to be the dependent variable. And we have to find the coefficients theta that come from doing linear regression and using the normal equation. Now, if you're not familiar with the normal equation means, I'm going to talk about that in depth in a little bit, but it just refers to a closed form solution for these parameters. Because there's another problem in the website in which you can solve linear regression using gradient descent. Now, I think this is an amazing problem because you're going to learn a lot about how to implement linear algebra operations within Python. We're going to use the NumPy library. If you've seen some of my previous videos, you know that I really like first doing some of the math under the hood, a solution that's under the hood with just using standard Python and then using something with the libraries. But for this type of problem, if we just went that route with just using whatever it is we have on Python, the code would be pretty long. So I'm going to go through the NumPy solution, and thankfully this is very intuitive because there's a lot of steps, there's a lot of ground, a lot to digest. So without any further ado, let's dive right in. Well, in this case, I'm going to give you the end of the story and then I'm going to tell you how we get there. So this expression that we have here, this is what it refers to the normal equation. And as you can see, it's just a function of the x and y. So that means that if you give me x and y, I can tell you what the optimal theta is going to be for linear regression just by plugging it in into this formula. And as you can see, this is very involved. We're going to have to transpose a matrix, multiply matrices, invert a matrix. Thankfully, when you hit this point, you'll be able to understand a little bit about how this works. Now, if you're like me and before you started getting into machine learning, you only knew about linear regression through high school math or maybe some of the starting college math, it was kind of confusing at first to see how these would translate into matricial notations. I'm going to give a brief overview of what linear regression means, but as with other videos, there's a lot of great resources out there that can explain linear regression in more depth than what I can do because linear regression, even though it's kind of a simple technique, it can get there's a lot of ways you can expand on it and you can pretty much build a whole field on it. If you look at some of the classic economics, pretty much all of they did with data was linear regression. So all of that is to say that linear regression is something that can go very deep. And I'm just going to give you some of the intuition behind it so we can see where this formula comes from. And once we understand where this formula comes from, coding it is not as hard as you may think. But first of all, we have to understand why this is happening. And again, it's always good when you're trying to learn about a new algorithm or any coding pattern to first understand where it is that it's coming from. How would you do it with pen and paper? Just the high level idea and then try to code it up. Because if you just plug in and try to solve a formula, uh, I don't think you're going to get much out of it. It's good for practicality. In reality, if you want to solve a linear regression problem, more likely than not, you will not do it as we're going to do it for this problem. But for educational purposes, this is great. So what does linear regression mean? Let's assume, just for the sake of argument, that we have a variable y. Let's call this the price. So this could be the price of a house. And we want to figure out how is the price of the house linked with the, let's say that this is the number of bedrooms. So intuitively, the more bedrooms a house has, the more expensive it's going to be. Now we know that in reality, there's not a perfect relationship between number of bedrooms and price. There's other factors such as location, number of bathrooms, stuff like that. But for now, let's just think about a simple word where this is true. What we want to find, the problem that linear regression solves is finding this parameter beta or theta, as we're going to use it here. And this parameter is what we're going to call the link. So how are these two things linked? So graphically, we had a graph like this. This is going to be X. This is going to be Y. If you were to look at the data set that related the number of bedrooms and prices, you would see something like this. A lot of these are supposed to be points. Some of them end up being lines, but this is what you would see. It's just scattered throughout. There's not a perfect relationship. But with linear regression, what you're doing is you're assuming that there's a best fit. There's a line, that's where the name linear regression comes from. There's a line that fits these points very well and can give you a good idea of how these two values are linked. Now, as I said, that's a very simple, perhaps it's what you saw in high school math. It's a very simple way of doing linear regression. Just one, what we call independent variable, this x's, linked to one dependent variable, the y. But as I said, in reality, this thing can be more complex. So another model, for example, could be, let's call this xp for number of bedrooms. So we could have theta v, the number of bedrooms, and then we could have something like theta L for the location. So for example, this could be how far away is it from downtown, which could influence the price. And we could have a lot of other variables, an assortment of big variables. So the best way to represent this, or rather a simple way to represent this, is with matrices. And so we can write this whole thing like this. This is going to be the idea of the model. So in an ideal world, what linear regression is saying is that in an ideal world, your y variable would be linearly linked to your x variables if you find the correct value of theta. That's the whole gist of it. Now, we know, as I said here in this graph, that in reality, that's not going to be true. So this is what we're going to call the model or ideal. And what happens in reality is represented by a hat. And this is what we're going to call reality, like the prediction. So when you talk about the prediction of a linear regression, you have this. When you're thinking about what happens in reality, what are the actual values of the y's that you see? The thing that show up here, you have to add something that's called an error term. And that's a random variable. That's something that is not captured by the model, but could influence here. And we can go very deep about what this thing means, how it should behave, what characteristics it has. For now, let's just say that this is why when you look at a plot like this in reality, your linear regression is not entirely perfect. It cannot account for all of the variation within these values. So the y has this thing, the epsilon, this error term, and the y with the hat does not. So that's what comes from the model and not. Okay, so we have visualized that. The whole purpose, there's a lot of assumptions, by the way. There's a lot of assumptions, as I said, that we have to have in order for this model to make sense. I'm not going to go through them. Again, there's a lot of great resources out there. This is just to explain where the formula comes from. But the main objective of linear regression, as a lot of machine learning algorithms, is to minimize a loss function. And this loss function, in this case, is pick theta, this is pick the parameters, so that you can minimize this thing, this equation that we have here, the difference between the y hat and the y. Now, the difference between the y hat and the y transpose multiplied with this. So you may be a bit puzzled here because most of the times linear regression is written something like this, with a norm. This is just a different way of writing it. If you try to do the math, you'll figure out that writing it in matrix form is the same as this thing. I'm just writing it in matrix form because it's going to be useful for when we're trying to derive the expression. But we know as well that the y hat has a definition. It's actually a function of theta. So the thing that we're trying to minimize, we're picking a theta to minimize, is this multiplication that we have here. Right? And the thing we have control over is the theta. X and Y are inputs. They're supposed to be known, come from data. You have no power over them. But you want to minimize these two things. Now, from here, from this minimization is where the theta comes from. Okay, so you may be wondering, why are we minimizing the squared of the difference? And why are we not minimizing just the difference itself? So let's go through a thought experiment. Let's say you have a model such that half of the observations are overestimated and half of the observations are underestimated. If you did the math, it could be possible that the error that you get out of it is lower than the actual error that you have. So for example, if all of the overestimations were, your predicted value of y plus 5, so half of the observations are such that you end up predicting this. And then the other half is such that you end up predicting this. when you add them all up, what's going to happen is that the average, on average, you're going to get the same y because the +5 and the -5 are going to cancel each other out. So then you would think, oh, I have a perfect model because there's no loss. But in reality, it's just that the laws are compensating each other. So that's not to say that your model is perfect. It's just that the errors are distributed in such a way that they compensate each other. And so this loss measure that you have is deceptive. Well, then somebody may think, well, instead of using then just the differences of stuff, why don't we just take the absolute value of the differences? And that's very valid. There's even machine learning algorithms that use this. It's known as the mean absolute error. The problem here is that, and this may not sound like a problem right now, but once we get into some of the deeper math, it's going to be a problem. The problem with this is that this function, the absolute value, has no derivative at 0. And because it doesn't have any derivative at 0, whenever you get to 0, you end up having kinks and kind of wacky problems that you cannot work with this. Ideally, because we're talking about an optimization problem, we would like to have a derivative pretty much everywhere. And because that's going to simplify our lives, the whole purpose, or rather the simplest way to solve an optimization problem is just to derive and make the derivative equal 0. And you cannot do that with the absolute error. That's why we go with the square error. But then you may be thinking, well, why are we using the square? Why are we doing this? Why are we not doing something like this? No, to the 4th or to the 6th or to the 8th. And that could work too. It's just that those derivatives are going to be more cumbersome mathematically. If you were to take the derivative of something to the square, right? If you were going to, well, I'm going to show you how to do it with the theta later. But if you take the derivative of something that's to the power of 2, the derivative is going to be a linear function. And we really like linear functions. That's part of the reason why linear regression is so popular. It's because we can work pretty well with linear functions. But we cannot do that with, let's say, a derivative such that you have a polynomial to the 3rd power. You can make it work, but it's just going to be a lot of work. So all of that is to say that's where the squared part of the square error comes from. So with that being said, let's go and try to figure out where this thing comes from. So as I said before, we're trying to minimize this thing with respect to theta. Whoa, with respect to theta. There we go. And some people just put, all of this divided by 2 or multiply by 1/2. It's fine either way because a constant is not going to change the result of the optimization problem. But for completeness sakes, I'm just going to put it here. So how do we find this? Well, to find the optimum, we're going to derive and equal 0. Keep in mind that we're working with matrices. If you're not very confident on how to do calculus with matrices, there's a lot of great sources out there, and you should go try to practice a little bit with those to get more comfortable on how things are working. So in order to derive this thing, first I'm going to expand this whole expression. So I'm going to put a -2 over 1/2 over here, and I'm going to expand this whole expression right here. So we're going to have x theta transpose times x theta that comes from here. Then we're going to have x theta transposed y. Then we're going to have minus y transposed x theta. And then we're going to have plus minus, and minus gives plus y transpose y. And all of that. That's what we have to derive. That's going to be our function. So let's group some terms just to make our lives easier. So we're going to regroup, we're going to rewrite some stuff. So we're going to have from this theta transposed x transpose x theta. And then going to have these two things are going to remain as they are. So x theta transpose y minus y transpose x theta. And then finally plus y theta y. Okay. Now we're going to take the derivative. And this is where you have to be somewhat comfortable with taking derivatives of matrices and stuff like that. So we're going to start deriving, and it's going to be with respect to theta. So we're going to have the 1/2 over here. So when the derivative of this thing, when you have the theta transpose, you just get rid of it and you multiply by 2. It's kind of like taking the derivative of a squared scalar. So we're going to have a 2 here. We're going to have x theta. The derivative here is going to be somewhat similar. We're going to end up with minus y transpose x theta. No, hold on. It's going to be okay, apologies. I made a mistake there. So it's going to be minus x transpose y because it's the theta transpose. So you just get rid of it and the x is x transpose. Here, because you only have theta and you don't have theta transpose, you have to transpose the other things. So you are also going to get minus x transpose y. And this term doesn't depend on theta, so we just get rid of it. And because we're minimizing, we want this derivative to equal 0. Now, you're going to figure out something very funny. So these two things can be grouped together, and they're going to be equal to 2x transpose y. And so we have a 2 here, we have a 2 here, and we have a 2 divided. So these twos just cancel each other out. And then this expression is going to be x transpose x theta going to be equal to x transpose y. And in order to get rid of this x transpose x here, we're going to invert it and pass it along to the other side. And that's going to be the expression that we're looking for. This is exactly this. So why can we invert this? Well, if you take a look at it, x transpose x is going to be a squared matrix. And if it's invertible, then we can solve this equation. If it's not invertible, then you run into a whole array of other problems. But this is the solution. This is the exact same formula that we have here. And now we know where it comes from. Again, for solving this problem, you don't really need to know where the formula comes from. You could have just coded it up. But as I said, for your learning, it's very important to understand where these things come from and why we have this formula in the first place. And if it doesn't click quite yet, try to go through the formula to the derivation by yourself. I'm sure you can learn something very valuable out of it. Okay, so now we're back to the original problem. And now that we know where the formula comes from, we can keep it here as a reminder. We can just code it up using NumPy, and we can be sure of how things are going to go. So first take note that the inputs we're given are lists of lists. And we want to use the NumPy operator. So we're going to transform all of this stuff to NumPy. So X, we're going to redefine it as NP array X. Y, we're going to do the same thing. Y is going to be NP array Y. And in the solution, you are going to notice that we have this reshape minus 1, 1. This is just a way of pretty much casting the actual NumPy shape definitions that we want. You can solve the problem without doing this, but this is a good practice. And explaining why would require me to go a little bit deeper into what NumPy does. Just for now, keep in mind that if you want to transform things to a vector, you should keep this in mind. Now, for simplicity, we're also going to define x transpose. And in NumPy, that's very simple. You just put a dot and a t. We could have also presented from this step, but this is going to make our lives easier. So now to calculate the theta, we're going to have to do a lot of multiple small steps. So first, we want to multiply x transpose and x. How do we do that? We're going to get xt dot x. When you call this function point dot on an NP array, you're just telling NumPy, hey, I'm going to multiply this thing with another matrix. and NumPy is going to check that the dimensions match. If they don't, then you won't be able to do it. Now that we have that, we want to invert this matrix. We learned in the previous video how to do that. So it's np.linkalg.imp, and we do all of this, and then we're going to get the inverse of the x transpose times x. Now, what do we have to do with that? We have to multiply it with the x transpose times y. So we're going to put a dot here. I'm going to say multiply this with x transpose, and then all of that multiplied by y. And then that's going to give you theta. So that's pretty much all there is. Somewhat straightforward. As you can see, just 4 lines of code. If we wanted to do this from scratch, it would take a lot of time, and this video would be super long. But for now, just keep in mind that this is how you would do it. The final step is that we have to make sure to round. In the instructions, we have to round our answer to 4 decimal places. Just ignore this thing that minus 0.0 is a valid result for rounding a very small number. That's just to say that you may see that when you're rounding the numbers, but it's not something that you'd have to do manually. Something that's going to happen is just so you don't get scared if you look at this thing. So with that in mind, let us round theta. And the way we can do that is we can overwrite theta, say np.round theta, and then the number of decimal places that we want to have. And the solution wants you to return a list. So whatever this theta is, it should be something that can be transformed into a list. We're going to flatten it, and then we're going to change its type to list. Do you need to do this? It's just to comply with the requirements of the code sandbox. If you're working on a project, you may not need to round something. This would be the official last step of the problem, but this is just to comply with the way the code needs to be formatted. So with all of that, we're going to submit the code. And as you can see, this is accepted, and it works pretty well. So there you have it. Some explanation why linear regression works the way it does, what considerations we have, why is it useful, and how you can code it up in Python. As you can see here, the code is very, very straightforward. It's a great exercise if you want to try and code it up on your own from scratch. I did that on C, and I almost lost my mind. But thankfully, you won't need to do that during projects. And when you're working with projects, you won't even need to do linear regression like this, because the inversion of this matrix can be very costly, and there's more efficient ways of doing this kind of approach embedded in the libraries. So thank you so much for watching this video. I hope you liked it, and I hope to see you on the next one.